what we're going to look at is the general idea of distributed computing, then some of the Distributed.jl basics. So this is then an implementation in Julia, but then the most part we will look at MPI. So what's the idea behind distributed computing? For now, we've seen how to optimize and run your application on one core. Then we looked at multi-core, therefore multiple threads that work on the same workload on one node. But as we've seen, we have a complete cluster of machines. As you also seen on the Ramses machine, there are a lot of computers, and it would be nice to parallelize further to all of these machines. Therefore, run your code on multiple nodes. Simply because if you have one node, one CPU, or in our case, it's a 2 CPU system, you can only get to the performance limit of this one machine. And before, as Shin already explained, there was, with time, you could just wait a little bit and the CPUs would become more powerful. And then after maybe 2 or 3 years, you would have double the performance just by waiting. But nowadays, this performance improvement declined. So with a system with the same number of cores in a few years, maybe the new version of the cores won't be like 3 times as fast, but maybe 10 or 15% in the best case. And then it's really nice to be able to scale to multiple nodes, and then you, if your application scales well, you can run your application on 2 nodes, 4 nodes, 8 nodes, 1,000 nodes, whatever is inside of the cluster. Now the question is, how can we do this? So in Julia, there are 2 main methods. There's this Distributed.jl. It's a built-in library for distributed computing. It takes care in the background of a lot of things for you. So it's rather implicit. You have still do some stuff, but there's also a lot of help from Julia. And then there's MPI.jl, which is a wrapper for these MPI libraries. It's a standard and used by many programming languages, and it is a dominant technique in on HPC systems. So it was designed for many decades to run well on compute clusters. Therefore, in the beginning of the 90s, when you would start to have clusters of multiple machines with normal operating systems, then the idea was, how can we make them your application distribute on all of the machines, and what is a good way, what are good abstractions to do this. So we will first take a very short look at Distributed.jl and then concentrate on MPI. Now it's rather convenient method. All of it is already integrated in Julia, and you have a master worker model. Therefore, you start Julia with some parameters, and it will spawn multiple processes. So now this is different from before, where we had multi-threading. So it was one Julia process with multiple threads, and the all of the threads could then access the same process memory. And therefore, it's internally easier, because then all threads can just access the same objects in Julia. Now we have multiple processes, and now Julia has to take care of communicating between these processes. On one node, there's technically still the possibility to use shared memory between two processes, but this also has to be set up and so on. Therefore, if you want to go on multiple nodes, then you have to use networking, and this also has to be set up by Julia in the background. And then if you want to communicate between your code, share some data, then Julia has to take care of sending the right data to the right processes. As explained, we have master worker model. Therefore, we have one main process that initiates then what should be done, what should be executed on the worker processes. And you can also use it interactively. Therefore, you say you maybe prepare some ranges of what should be done, some input data for the workers, and let the workers initiate the functions that they need to do the work. And then you basically tell all the workers what they have to do. And in the end, you fetch the results from the workers. That said, it has a higher overhead than MPI because it's also more an abstraction, more abstracted what is happening in the background. So it's more implicit than MPI. How does it work? You start up Julia, and you tell Julia how many processes you need, and then Julia will take care of spawning these worker processes, and everything is then communicating over a communication network. And then the main process is the one that you control, that you can also control interactively, and then you distribute the work. Then you say, for example, worker 4, execute this function, and then you can, your main code runs further. You will get a future object, and then you can call fetch, and then fetch the result from the worker once it's done with the computation. So here is an example code. We load the distributed package. We can also ask how many processes we have, and we can also add some processes, and that will be spawned. Then we can have, with the add_where macro, tell all of the workers to initiate some functions, to define something, to import some packages. Therefore, then all of the functions that you need for the computation are actually available on the workers. So they need to have the same things available. And then you say spawn F, and then it will create a task that will be executed on one of the processes. You will get a future, and then you could do something else, maybe do computation on your own in the main process. And then later you can fetch the result, and then it has to be in the background. It will then be transferred over the communication network. So you had a question? Hmm. I meant interactively because it's just like a normal Julia process. You can also use it in a REPL, and then it just in the background knows, okay, I also have some of these worker processes, and then you tell, for example, with this code, okay, I have this function with this input, please create this task and execute it on a different worker, and then you can later fetch the result. No. Mhm. There are also some higher level tools, for example, this parallel map with the map function. you give it a function and some input data, a collection, for example, and then every element will be processed with the passed function, and you will get as a result then a collection back with the result elements, and with the pmap function, this will then use the Distributed.jl mechanism to distribute all of these function calls to the workers. They will execute it, and then it will automatically fetch the results. So what you have to keep in mind is that in this case, also there's no guarantee about the order of the function executions for the elements. So it has to move, split up the input data, distributed to some of the workers, and then you basically don't have a guarantee what is executed when. Therefore, your computation has to be safe in that regard. There's also this add distributed macro, where you can also pass a reducer function. It's optional. If you don't pass it, then you will simply get back all of the results as futures that you have to fetch, and then you can reduce on your own with your own function afterwards, or you can specify this a reduction function here, and then the results of the loop that you specify will be reduced automatically by this reducer function. Therefore, you see there's the distribution of the work and is implicit. It's taken care of by Julia. You can also more explicitly, for example, specify what task should be executed on what worker. So there's much more also about what data is transferred, or you can also create remote channels where you can send some data to some other workers. But this is what we're going to look here right now. So we will now go over to MPI. So in the Julia documentation, you can then find all the details. Yes, please.
Similar to like a task.
It's so the concept is quite similar, but if you look at the documentation, you have to be a little bit more cautious about the accesses, because for example, if you have some global variables in your main process, and then in your task you access this data, this is possible, but only read-only. Therefore, if you would change it, then it would only change in the context of the worker, and it would not transfer back to all of the workers in the main process. So there are some caveats also in how the data is distributed. Now, let's continue with MPI. And I hope after Shin set the expectations quite high, we can check if we can fulfill this. Now, it's industry standard. That means there's a specification of interfaces, how it should work, what you can expect if you call these interfaces, and then you have multiple implementations of these interfaces. So the main idea is that we have explicit communication between our processes that partake in this computation. And the general idea is that we have single program, multiple data model. This means we have usually one binary, one program, and this is started multiple times. maybe on one host, maybe on multiple nodes, and then they can communicate between each other and distribute data or compute something, and then in the end you can write back your result. And since it's the same program, the question would be, how can you differentiate the computation? And the idea is here that you have overarching framework that starts these processes, and then every process gets a rank, therefore an ID from 0 to some maximum number, how many tasks you are starting. In this case, task means process. So how many processes you are starting. In MPI, you also say rank to them, because the rank is the ID of the process, but you also call the process simply a rank. So yeah. However, this also means there's not it's not so suitable for interactivity. And MPI.jl is basically a wrapper for MPI. As explained, there are multiple implementation of the specification, and they are implemented in usually C and Fortran interfaces for these libraries, and then also other program languages can import these interfaces, these libraries, to make this available to the programming languages, as for example in Julia. And what's also interesting is that it's internally it's a layered framework where you have one thing is the interface, but then it's also the communication layer. It can then communicate over different protocols, normal network protocol, TCP/IP. But in HPC, we also have these other network implementations with quite expensive cards that have lower latency and higher bandwidth, and then you have these special drivers and so on. This is also taken care of by MPI in these communication driver layers. But as a programmer, you only see this MPI interface that was specified. Now, how does a program look like? We have our SPMD style program. Therefore, it's one code for all of the ranks. And when every process starts, it can ask the framework, okay, what rank am I? And then differentiate what it should do depending on the rank. And rank 0 is always the rank is simply the ID of the process. They get an ID. From 0 is usually the root or master rank, whatever you want to call it, that orchestrates a little bit the calculation. For example, usually if you want to print, you have a result of one number and you want to print it, but the calculation is distributed over multiple processes. Usually you will then send the partially results back to the first rank, so rank 0, and rank 0 will reduce it and then print it instead of every worker printing their partially result or something. Therefore, usually say rank 0 has a special role of orchestrating the calculation or distributing the input data, something like this. So this is just a typical model of programming this. And then you could say we have some function that is doing some main work, and then some other function that is doing this worker work. And in the actual execution, we will have, in this example, 4 processes, 4 ranks. And then rank 0 will do the master work, and all the other ranks will do the worker work. Yes? They are just dummy words. If you say there is a function, but it doesn't matter what it is doing. It just matter that it's there. It's just a dummy word, a replacement word for a function name. It's like you want to do an example for addition, but you do not care about what you add. Then you say, okay, I'm just doing foo plus bar, because it doesn't matter what it is. What's the importance is the function, so the addition, but they're just stand-in words that are used when talking about programming. So it's there's a Wikipedia article about it. It's called meta variables. It's quite funny. In other languages, they use different words. And I had some code from an Italian colleague, and I was wondering, what are these words? What do they mean? And then I looked it up, and they are like fu and bar, but just in Italian. And apparently they are the names of Disney figures that they use for the names of the variables. It was funny, okay. But these are just some functions that do something before, then you have your master work, and then use something afterwards. Exactly. So we have one code. You will get one program. It is spawned multiple times as multiple processes, but then it differentiates by looking at its rank and then doing slightly different things. And yes? Well, you can use libraries, packages, and so on. So you can distribute it to multiple files. However, you want to have it as a Julia program, but then you have one main script. So technically, it doesn't have to be, but it's there's some advantages. It's you know that you execute the same thing, so it's easier to reason about what's happening, and so you don't have to compare multiple code, but you see that in one code how the program should run, and then see the differences. Therefore, you have, and usually you program it to be agnostic about the total number of processes. Therefore, ideally, your code can be executed with by specifying in the end, okay, I'm starting 2 MPI processes, and then the work will be distributed on 2 processes. Or you can say 128, then it will be split up to 128. Or I want it to be on 10 nodes, then it will be split up on 10 nodes. And your code stays the same because it just looks up at runtime, how many processes do I have, and how should I split up the work.
Example, so one process would be like computational one column. You would that from like process, right?
Yes, so let's say we have a lot of columns. We have our program wants to have 1024 columns of the image. And then at the startup, the program will look at how many ranks were started. I maybe have 2 ranks. Then it will be split up in 2, and each rank has to do 512 columns. And then you have to communicate between, for example, the master rank 0 will say, okay, we have so many, and then you do, and then for example, every regular worker expects to receive how many or which columns it should do, and the master rank decides how many or which columns each rank should calculate. Therefore, exactly, and you start the program with MPI, and then you have a parameter how many processes should be spawned. So this is not, it is outside of your program. You do it on the command line. And inside your program, the first thing you do is what is my rank? and how many ranks do we have in total. There's a function you can call, and then you will get it back from the framework, because the framework knows how many ranks were spawned. And then this framework takes care of this communication. They can be spawned on one node or multiple nodes, whatever. It's done automatically. And then the idea is that these different ranks can communicate by sending messages, sending some data. Now we have some very important functions that that are always used. So MPI init, this is at the beginning of the program to set up, just to initialize the framework and so on of your rank. Then MPI finalize, you would do this at the end to clean it up, to be proper, a proper program. Then you can ask what is the number of ranks. You can ask what is my own rank, and then you can send and receive messages. And in the beginning, we have a communication group, and there's a default one, MPI com world. This is just the main group with all of the ranks that were spawned in this instance, for example, in your job. Therefore, you say, I'm starting my job and allocating 2 nodes. Then you have 256, and you specify how many ranks should be spawned, and then you have 256 ranks, and they are all in this default group. And then there are some messages that where you can say, I want to send a message to one certain rank, but there are also some operations where you specify, I want to do it for all of the ranks in the group. You can also it's some more advanced functions where you can split it up and have subgroups where you have messages that only go to subgroups and so on. So to structure your calculation. But this is some advanced features. Let's take a look at an example here. So in this case, we have this MPI exec, which basically is the starting of the framework. Then you tell it how many ranks you want to spawn and what is the command. So it doesn't really know about Julia. It only knows that there is some computer program that knows MPI, and I will spawn it 4 times. And then it will start to communicate over the implementation, and then it will do the magic in the background. But you then specify which command should be started. And we see here it is the same script for all of the processes, and then we get some output. And then here we see our start. We load the package, do MPI init to initialize the framework. And then we say, we can ask our own rank, com size, how many ranks do we have? Then we have a nice message that we want to transfer, where we also include our own rank and what we got back for the total number of ranks. And here we have to do a little bit conversion of a string object to a vector of chars. And then we have a differentiation between what is rank 0 doing and what is the other workers are doing. No, it's the other way around. So this is the every worker, and this is what the rank 0 is doing. It's 1 character difference. Therefore, all the other workers, they will use MPI send to send their message using our main group. So this is the com world, our world group, and the destination of the message is 0, therefore rank 0. And rank 0 will first print its own message, and then it will iterate over all the other IDs that it knows, because it asked how many do we have. So its own is rank 0, and it starts from 1 to the end. Then it expects to receive a message from this rank. So it says, I'm having just some buffer where I write the message that I receive into. And then I say I expect a message from a certain rank, and then I will print this message that I got. So we see that it's quite explicit. We specify here which what we want to send and where we want to send it. And as we see here, it's agnostic about the number of total ranks. It asks at the start how many ranks do we have, and then it just you can start it with 4 ranks or 8 ranks or whatever many ranks. Yes.
What writes is MPI exit command in the Slurm script. Do I have to load an MPI module first, or what? Will this MPI module then be taken from Julia?
So if you just install MPI.jl on your local machine, it will also install some MPI libraries that will work. But on you can then also tell it to use a system library. But on the cluster, it's set up in a way that you load Julia HPC. Actually, I'm not sure you even have to do this, because Julia HPC should also include it, but it doesn't matter. And in this case, we do not run MPI exec, but we run srun. And this is then a Slurm command that will talk with Slurm. And then in Slurm, you can say, I want to spawn 16 tasks. And then Slurm will, because MPI also has to know where it can spawn things. And with this Slurm command, it knows about MPI and then takes care of knowing on which actual compute machines you can spawn these tasks. And in this example, we only specify the number of tasks, but we do not specify the number of nodes. Therefore, we only say I want 16 tasks, and they could spawn on 16 different nodes, but they also could spawn on one node. So it isn't specified in this parameters. You can add more parameters to limit what Slurm should do. You could say I want it to be on one node, and I want every task to have one CPU core allocated, and then it will in total allocate 16 cores and will spawn 16 MPI tasks. Oops. Yeah.
One for Slurm, another one for MPI, another one is the Julia program is doing the real work, like the real program. It's like the script for running
I mean, the MPI script, you can also specify here what it should do. I mean, this is the MPI script that we are calling, and here we already also specify the communication.
Change that based on the program that you're in, because I mean, from what I see, it can be themed, like, or different, for running different kind of computations, right?
Well, it highly depends on what your application and your algorithm is doing, because you could program an abstraction and then say in the beginning, I just have a number that is distributed to the workers. Then you have some function that is getting this number and doing some work, and it returns one number, and then you return the number to the rank 0, and then it will be printed or something. Then you would have an abstraction. But if you have, for example, a simulation of physics simulation, for example, then there would be different communication patterns than in a different calculation, and therefore you couldn't really reuse this communication code for this other application. And here again, we also see that we use srun, and we just tell it to run Julia with one script. And then there will be then 16 Julia instances executed, and then they start communicating with each other using MPI. Let's take a look at what kind of communication can be done. So first is a point-to-point communication. And here we have the MPI send function. And as we've seen, we have to give it some data and tell it in what group we want to act. So usually it's just the main group, the default one with all of the ranks. And then we tell it what is the destination rank, and there's also an additional tag parameter. This is just to differentiate between different messages. So this is for more complicated communication patterns. And we have to think about the behavior in this case. For this function, there is not really a guarantee that it will not block. It can block, and then it will wait until the receiver calls receive and receives the complete data that we sent. And we will see that this is an important thing about this particular function. And then we have the counterpart. We have the MPI receive function where we have a destination buffer, and again here a source parameter from who we expect a message. It can also be this default constant MPI any source. Then we will accept a message from any other rank, or we can explicitly say we wait for a message from a certain rank because we know of the communication pattern. Right now we should receive a message from rank 3. And here again, it will also block until we actually received the message. So there's a certain matching going on in MPI. When does the receive function is satisfied with the message that it gets? It can, because the order of messages can be scrambled in the network. So there are no guarantees in the networking. They could overtake each other, even if they're sent in a different order. So therefore, also in the programming, it could be that your actual program will, in the background, receive the messages in a different order than they are sent. Therefore, there's a certain match logic in the MPI functions. And here we see it will match if these three parameters match. Therefore, if we actually get a message that has the correct source rank, the correct tag, and the correct communication group that we expect. You can imagine the in our example code here with the greetings messages, we explicitly tell what from who we expect the message. So we do not take the first message that we received. It is stored in the background until we actually ask for it with the receive function. And in this case, in the calls of the receive function, then do the get the message once it's received actually by the program, and not take just the first one that the program receives from a different rank. Therefore, they could arrive in a certain order, and the other messages are stored, but we only get it the one that we expect the first. So we first expect the first message from rank 1, and then from rank 2, and then from rank 3, even if the message from rank 5 has already arrived. Yes. Yes, the tag is optional, but you can, if you have a more complicated communication, then it can be useful to differentiate. So in a different example, there was this default value for source with any source. And in this case, here we see the order is correct because it is we asked for the messages in this order in the for loop because we always fetch them from our received messages in this order. If we use any source, then we would see it in the order that they arrived. But then we also have to take care of that we ask and call the function in the exact correct number of times to get all the messages. If we call the function once more, then it will maybe wait for a message that never arrives, and then it will block forever. This is why there is this matching going on to get the correct message at a certain point in your program. Also, you have to be careful about the type and the size of the data. Let's say we are sending an integer, but we expect a float. Then MPI doesn't care about it. It will just put the bytes into our destination buffer, and then we interpret the bytes as a float, but then it will be a wrong number because it was we sent an integer, and then the format is different. And for example, we are sending 100 bytes, but in our buffer we're expecting 2 bytes. Then this will be a problem. So this is a very explicit way of communicating. So I've talked a lot about the order of messages and so on, and with this point-to-point communication, you have to think about the order because it can be that you will end up in a deadlock where you wait for a message that never arrives because a different rank that should send the message is waiting itself for a different message and so on. So you can end up in the lock here. And this is this can happen if you have chains or loops inside of your structure of ranks or communication structure. And this is similar to maybe you heard of the dining philosopher's problem. This is a similar problem. therefore, we have to make sure that this doesn't happen. And this can happen by accident. So here's an example. If we have here a number of ranks, and every rank first sends and then receives, as explained, the send function can block until the message is received. But if every rank calls send and no one calls first receive, then it could happen that there's a block happening, and then it will lock up. Because for this blocking to not happen, the receiver has to call receive. But since they themselves are blocked in the send call, the complete, all of the ranks basically are stuck in send. And what you can do, for example, is a manual communication scheduling where you think about the order of the send and receives. So it will not happen that there will be a lock. In this case, it's quite simple. For the ranks, you alternate between the send and receive order of functions. So the even ranks first send and then receive, and the odd ranks first receive and then send. And then this will prevent this kind of lockup. Luckily, there is also an MPI function that basically combines send and receive, and then it takes care of this. So therefore, at this point, if every rank just calls send receive, then it's a combination. You tell it in the parameters what you want to send and where you want to receive the message, from where you want to send to, from who you want to receive. And then send receive will do it in a way that it can't lock up. So this is not very dynamic. Therefore, we can send some messages to distribute, for example, the input parameters for calculation. Then you can do some work. And then once you're done, and the workers, it could be that the workers take a different amount of time for the different workloads that they have. And then once they're done, they can then send the results. And then, for example, the rank 0 can then gather all the results back to for example, reduce the partial calculations. But sometimes you want to synchronize all of the ranks. And for this, you can, for example, use the barrier function. And this one has only one parameter, which is the com parameter, therefore the group of ranks. For example, if we use convert, then all of the idea is that all of the ranks will call MPI barrier, and they will wait for the last one. So they will block at this function until all of the ranks in this our communication group reach this point in their program to synchronize everyone. And once everyone called the MPI barrier function, at this point, it will be released, and then they can continue. For example, you have a simulation with a certain grid and you split up the grid, and then every rank takes care of a portion of the grid, and then doing some local calculations, and you're calculating one time step. Then before the next time step, you maybe want to have a barrier. Therefore, all of the ranks stay in sync. Yes, and here's an example. It's with for time measuring. Okay, let's take a look at a more real example. In this case, we have an integration of a function. Therefore, we want to calculate the complete area under our function, and we can split it up in regular stripes. And then distribute these stripes to our ranks, and later then gather again the results, the partial results, to sum up these stripes to get the complete area under our function. So this is not the best way to integrate, but it's a nice example. And here we can think about how to calculate this area if we have one stripe with a fixed width. So every stripe has the same width of h. We have a start and the end part of our complete portion of our function that we want to integrate. So we have a and b. Then we split it up into n regular stripes. And then we have a stripe width. And for one stripe, the area is then, we can calculate the area by this little formula. We get the first value of our function and the second value. And we can think that if we add them and look at it as a little rectangular, then we have to split it up. And then we get basically the area of this part of the function. And if we look at all of the portions of our function, so we have the multiple of these little stripes that have the same width, then it's basically our start of our function, and then the next part of the stripe, the third, the fourth, and so on. And if we rearrange a little bit the formula, what we in the end have to do to compute the total area is we just have to sum up this sampling of the function. And for the first and the last elements, here we also have to divide it by 2. But for the inner ones, we don't have to do this. We sum it up, and in the end, we multiply it by the width of our stripes. So in the end, what we can do, if we have a very, so obviously, the more stripes we have, the more precise our integration will be. And the number of stripes doesn't have to be the number of ranks, but it could be way higher. And then you just take one portion with, for example, 500 stripes for one rank, and then you can distribute the sampling of the function to the ranks. Therefore, we split up our work. We compute the area of one portion of our integration. we split it up into multiple portions of our integration, and then every rank gets a portion. Calculate the this partial area, send it to in the end to the main rank, which then will reduce the partial results to the main result. So here is just this serial code for one portion of the integration. We have our function, we have our start and stop coordinates, and then we have the number of steps and the width of our steps. Now what we have to do first in our program is we get, so in this case, it has some arguments on the command line. We can give it the start and stop of the complete integration and the number of splits. Then we again get our rank and the rank size. And in this case, we don't even need to distribute the input parameters because every process gets them over the command line, and it receives its own rank. And this way it knows rank 0 has to take care of the first part of the computation, rank 1 has to take care of the subsequent portion of our computation, and so on. So every process in this case already knows everything that they need to compute their partial calculation. So we have the number of total ranks and steps. So we know our local steps, our local A and B. And we have our function defined in our program. Then we do our calculation. Therefore, every rank is doing their part of the calculation, their local part, and then rank, the worker ranks will send their result back to rank 0. And rank 0 has then has to accumulate these partial results, and then in the end can print the total result. Yes. It just parses the arguments from the command line. I think it's a Julia function, isn't it? Yes. Let's look at some other functions that will have a certain improvement, which are non-blocking point-to-point communication functions. And as explained, for the normal send and receive functions, we don't know if they will block or not. They could block. And if they block, we have to wait, which is bad, because in this time we can't calculate. Therefore, if you want to really optimize the performance on of your application on a cluster, it is the main idea is that you remove all the things that you do not have to do for your calculation. And waiting is one of these things that you don't have to do. Waiting does not contribute for the calculation. It just extends the runtime. Or at least you can't forward your calculation because while you're waiting, you don't calculate. And you could have calculated if you would not have to wait. Therefore, there are also non-blocking version of these functions. And the idea here is you send something and then you get an object that you can use to ask if the send was completed or not. This way you can initiate the sending. The sending will be done in the background, and then you can already do some other calculations. You don't have to wait for the send function to unblock. This way you can overlap the communication and your calculations, which is a huge improvement. Yes, and you can also mix, you could use the non-blocking send, but the blocking receive. Because in the background is just message that you receive, and then the receive function will pick up the message from the received messages. Now the function itself is quite similar. You just it's just called isend, and you it returns an object that you can use for to check what's going on with this communication. And because your ranks could have different workloads, or one rank could be on a different node that is slightly slower or faster. There could be differences in the timing. Therefore, this is why the waits happen, because of you have an uneven distribution of the workload, or because for some reason one of the ranks is slower than the other. Therefore, then you can use this for overlap. You can, for example, say, okay, I'm already done with my work, and the other rank should also be done with its work, and now I should receive a message. But maybe the other one is slower and did not send it yet. Then you can do I receive, and in the background it will then wait for the message to arrive. And you can do some other stuff, and later you can check, did I receive the message or not? And for this we have these two kinds of function. With the test function, it just checks is it completed or not, and it returns the result immediately. So it's true if it's completed or false if not. And you give it this object that you received from the isend or iReceive functions. And we have the wait function, where you, for some reason in your program, you don't have anything to do, and it's critical that you get this message, and else you can't continue your calculation, and then you can actually block explicitly and wait for the completion of, for example, the receive of the message. There are also some helper functions where you can have, if you have multiple messages or communications going on, you can test all, or test if only one of the of these objects is, or communications is completed. And the same with wait. One example for this non-blocking communication is if we have a grid where we do some computation, for example, stencil computation. Therefore, we have this calculation where we have our input data, and we do have some output data of the same size. And for every element in our grid, the output data is defined by the input data at the same position and the input data around this position. Therefore, we get we have to look at the input of our previous state and take these elements and then compute the result for this position in the output state, and then we basically move over this grid and compute all the elements. Now, how do we split this computation up? We can split up the grid, and every rank receives a stripe of our grid. Therefore, every rank has a certain portion that they have to compute, and usually you do this in multiple steps. So you have, you could also look at it as time steps. You always have the data, then you compute the complete result for the next time step, and then you use this as an input for the next time step, and so on. Therefore, if you want to compute the next step for our portion of the complete grid, there's one area where we have all the needed data of that we already computed, or that belongs to us, to compute the results for our portion of the grid already here. But at the border, there will be some data that is missing because this belongs to a different rank. This is then called ghost cells or halo, because this is like a halo area around your portion of the grid that belongs to a different rank. And to compute the element at the border of your portion, you need some input data from the other ranks because it belongs to the other ranks. And in the previous steps, they computed their portion, therefore they have the input data at this certain timestamp. And what you do in this case, you have some portion where you have all the input data and you can calculate it. And for the border cells, you need to receive the data from the other ranks there. So there's some communication has to go on. And at the same time, the other rank has the same problem because they also have a border and they need some input data from your border. Therefore, what can we do? We can initiate the communication first with non-blocking calls. Therefore, we have our initial data, and we can send the part that the other needs that we have, and we expect that we receive the part that we need that the other ranks have. And because communication takes a while over the network and so on, in the meantime, we can already compute all the cells where we already have the input data because it belongs to our portion. Then we happily compute our everything that we can. And once we are done with this, we can check if we already have the data that we need because we expected to receive some messages. And then once we have the data that we need, we can compute this halo region at our border. And this happens in one of the time steps, and in the next time steps then again, because usually you then do calculations for multiple time steps. Okay. As you can already see, if we parallelize computations, there's also always the question, how do we split up our work? Because depending on this, it can happen that we have more or less communication to do. So communication is basically a side effect of splitting up, distribute the work, and we have to communicate because the other ranks do need the data. And then we have to think about how can we split up, for example, this grid or some other communication, some other calculation in a certain way to reduce the communication between the ranks. Okay. Let's take a look at another form of communication that is supported by MPI, which is collective communication. And here the idea is that we have some functions that involve all of the ranks or a subgroup at least. So before we had one point-to-point communication where we explicitly sent messages to certain ranks. For example, in our stencil computation, your border data only concerned your direct neighbors of your grid, of your portion of the grid. So you didn't really have to communicate to all of the ranks, only to your neighbors. And in this case, we want to have some communication between all of the ranks. So this is useful for synchronization. We already seen the barrier function, or to move some data. For example, we have some input data and we want to distribute it to all of the ranks. Or we even can do collective communication computations when we have some results and want to reduce them. First, again, this barrier function, and here you see it graphically. Every rank calls barrier, and they all basically wait for the slowest of the ranks. Once the last one, also called barrier, all of the ranks are released and can continue their the computation again until the next barrier call to synchronize the calculations. Now for the other collective communications, here is visual representation. And what we see here are the ranks in the Y direction and some data in the X direction. So here we have rank 0, 1, 2, 3, 4. And there's some data. So in this case, rank 0 has some data, and it wants to broadcast the same data to all of the other ranks. So there's a broadcast function, and for the collective communication, every rank has to call this function because it's collective, so everyone has to help. So it will also synchronize the ranks. For example, at the beginning, there is some input data, but only the first rank read it from a file, for example. And then they can have one of the parameters that is interesting to all of the ranks. They can broadcast it to all of the ranks. Next, we have the gather. And in this case, all of the ranks have some data, different input data. And there is one special rank that at the end of the gather function will receive all of the input data of all of the ranks. For example, rank 0 wants to receive partial results, and it's a float. Then all of the ranks say, here's my float, and I sent it to call the gather function. Here is my part, and the rank 0 then receives a vector of the floats. And the other way around is also possible. This is the scatter function where for example, rank 0 has a number of values, and then they are distributed to all of the ranks. And then we have some versions of these to all gather, make sure that not only one rank receives all of the data, but every rank receives a copy of all of the data. If for some reason every rank needs the partial results of all other ranks, then you could use this. And there's also this all-to-all version where everyone has some data and needs to distribute a certain portion to all the other ones. And you see this is basically transposed here, this array. So we have here the broadcast, we have a buffer, and we only give it a group because everyone in this group is involved. And we have the special rank that decides which data has to be broadcasted. And for rank 0, this is then the sended data. And for the other ranks, we give it here the place where it receives the data. It is broadcasted then from the root rank. And again, all of the ranks have to call this function. Here's an example for the scatter function. Again, we have our root rank that has these the vector of data that has to be distributed, and the other ranks specify this receive buffer here that to receive their portion of the data. And similar, the gather function where then, for example, the partial ranks have their partial results and send it to the root, and the root then gathers all of the partial results, and then it can iterate over the vector of partial results to do something with it. And we can also combine this with a computation. There are some computations predefined, for example, a sum. You can, you can specify which function should be used for the reduction, and then all of the partial results will be reduced to only one value that is then received by the root rank. And in the background, it is not the case that all the messages are simply sent to the root rank, because you can optimize this. If you think about that you have a calculation that you distribute over thousands of nodes, and everyone has to send their message to the root rank, and then the root rank receives it and then just calls sum over all of the elements, then this basically becomes a communication bottleneck. And we have this interface of reduce, and you could implement it this way, but you could also do it smarter. And this is then the task of the implementation of MPI, to do it smarter. You could you can have some patterns in your communication where you send some of the partial data to some ranks. They do the reduction of these values that they receive, and then they send their reduced value, which is then less of data, to another rank. And then this means that many ranks participate in the communication, and the computation, but in the end, the final result will end up at the root rank. And this way you can solve this bottleneck problem of this kind of computation and communication. Here's also a variant of the reduce function or reduce, where then everyone gets the result at the end. And we also have a scan function where we do not compute the sum of all of the elements, but we have a partial sum. So the first partial sum has only one element, the second has two elements, the third 3 elements, and so on. So in some algorithms, this is very useful. Here we also have the signatures for the reduction function. And this is basically the same as with the other collective functions that we've seen, but we also additionally specify an operation. And they are then some operations that you can use, for example, the addition. So we've seen this matching of the point-to-point communication functions, which is useful because then there could be different orders of the sending and receiving in the for the different ranks. For collective functions, it is expected that the order of these collective functions is the same for all of the ranks, because it also functions as a synchronization point. So therefore, it has, if all of the ranks participate in the same function, the same thing, then all also have to call the same function. And then they also have to call the same communication group, or do this collective in the same communication group. And then they are in MPI, in the interface, in the specification, you will find what was it, 200 or something functions with variations of these main principles. For example, you could have different amounts of data in gather and scatter that you want to receive from different ranks. So it can be, you can also implement more complicated communication patterns. And now at the end, we can also get back to our trapezoid example. So we had, after we every rank computed their partial result, we used this point-to-point communication with the send and receive to send the partial results back to root. But in this case, it's also a nice way to just use the reduce function, where everyone sends their result value, and then MPI will take care of the reduction, and the root rank will receive the total result. Now, as a summary, we've seen the message passing interface, and this interface, as explained, it comes from the HPC community, where you have the need of this very efficient communication between the nodes in your cluster, because if you have very latency sensitive computations, then you and communications, then you want the communication be as fast as possible. And as we all also see that MPI with this message passing interface, it's quite explicit. You always have to specify what kind of communication you're doing, what data is communicated. And but this also means that this is less of an abstraction and a little bit more work maybe to specify explicitly what communication is done, but then also the overhead of the communication is reduced. And we have this MPI.jl wrapper that wraps this framework that is used on HPC clusters and can then in the communication layer beneath in the libraries can also use these low latency, high bandwidth hardware that we find in HPC clusters. And MPI yes, also has some other functions where you can have kind of a shared memory thing where you have a portion of memory, for example, an array, and then say, okay, this other rank is now able to access it. And then they can, for example, write some results in it. And then you have to specify a start and a stop of this process. And at the stop, there's a little bit synchronization being done between the receiving and the sending rank. And then MPI takes care of updating the values on the receiving side, which is a kind of a distributed shared memory thing. So there's some more additional capabilities in the MPI interface than what I presented here. Yes, in the end, acknowledgements. Do you have some questions at this point? Yes, please.
Like simple things like the sum or so, or could I define my own reduction function?
There's a certain set of functions predefined. Shin, do you know if MPI.jl also wraps the custom functions?
For basic operations, I think yes. You can also define your own customized operations to do this reduction. And in the worst case, I mean, if the reduction is really, really complicated, you can still create your own. And based on my experience, I don't think there will be lots of performance loss. Yeah, if you are using the HPC cluster, because the communication between compute nodes can be very fast by going through the so-called InfiniBand. It's a very fast communication channel, so no worries. And there's no race condition. Yeah, this is my point. There's no race condition. You have correct result. This is very important.
Okay, that's a good idea about what Shin said yesterday. So there is no NUMA problem, no race condition problem. There's a deadlock problem, but communication. And the reason for this is because we do the communication explicitly. We explicitly say, okay, this portion from my data, from my memory has to be copied to this other portion. And then we already have an explicit communication here where, for example, in the NUMA problem, it exists because there's hidden communication that you do not see because the data is stored in different memories. And this produces this performance difference for the NUMA problem. As well as for the race conditions, because we have this explicit communication here in the MPI model. This is why it's you don't have these problems in this case. And as a plus, you can then scale over multiple nodes. Okay, let's go into the break and then take a look at the exercises.